absorber with the help of graphene material. And we will also see how we can develop the graphene in the CST using the macros. Okay, that all we are already covered. And apart from this absorber, we have also covered the polarization converter. Okay, in polarization converter, also here are two types of based on their result, we can categorize as two types. One is the multi-band polarization converter and another is wideband polarization converter. For all these four type of absorber and polarization converter, we have uploaded the respective papers in the canvas. You can see, you can watch all these papers in the canvas. Okay, if you have not accessed these papers, so that's why we have already uploaded the PDF version of those files. And after that, in the yesterday lecture, we have also see the how we can create a array structure. That we will also see how we can make 1x3 array. Then how, with the help of this 1x3 array, how we can create a 3x3 array. And we will also see for the unit cell structure in CST, we have to make a fluctuate port for the excitation and for the simulation point of view. But when we are talking about the array structure, any type of array structure, then we have to make it using the waveguide port in CST. So in yesterday class, we have designed the unit cell structure, and also we have designed 3x3 array structure for the bending analysis, for analysis of the conformal. Okay, and all these things we have already covered. In the last hands-on session, we will also see the basics about HFSS, or we have also seen the how we can import our CST design in the HFSS, how we can export it from CST and then import it in HFSS. That we will also cover in the last lecture. So, and in today's hands-on session, we will directly go to the HFSS software, and first 1 hour we are covering all these designing part, because in HFSS the major tricky part is designing, because its designing is totally different with the CST. Okay, so first 1 hour we will cover the designing process, how we can rotate the structure, how we can make a mirror, how we can develop different shapes of structure, and what is the position of our structure, because it is very tricky in HFSS. Our designing position, from where we have to start our design, this is the main part. Okay, that we will cover. And after this 1 hour session, we have our validatory session. So we just take break for this hands-on session, and we will cover our validatory session, and after that we will resume our hands-on session from 3:45. Okay, so this is the overview of today's session. So I just share my screen, and I will directly go to the HFSS software for the designing part. And after this 1 hour and after the validatory session, we will make a unit cell in the HFSS software, and then we can see how we can make a boundary condition and how we will design our how we can simulate it using the fluctuate port in HFSS. Okay, and in the last 20 to 25 minutes, we will take the query session for all these hands-on session. In all those 8 days, whatever query and whatever questions, if you have any, then you can ask in the last 25 minutes. Okay, so let's start the session. Okay, I think my screen is visible now. So we will just start with the answers. Now, I have my lab mates, Tawfiq. So we will combinedly take this session for this HFSS. Okay.
Okay, so good afternoon, everyone. We can start creating our unit cell design on HFSS. Okay, we will simply start by first selecting the project and inserting the HFSS design on HFSS itself. Okay, so okay, now we can see the basic interface of HFSS. Okay, so in HFSS, as sir said, we can create the unit cell design in two methods or more than two methods if you think. Okay, so in CST, if we take reference to the CST, we design the unit cell taking the origin as the center of the unit cell. We can simply do that in HFS itself. Also, we can take at the edge of the unit cell as the starting point as well. So we will simply start by taking the origin as the unit cell center. As you can see, there are a few options in HFSS. We will first start by going to HFSS and then going into the solution type. In this solution type, we have to select the option model. This model option is selected because we will not be able to assign the Flockweight port in terminals option. So we'll have to do this in the model option. So we will do this okay. And since we are dealing with the terahertz frequency, we need the dimensions to be in micrometers. So we will simply go into modular and then we'll go into units. In units, you can see select unit section and we will simply do this. We will select micrometers as our units, okay, and we will rescale to the new units every single dimension in HFSS. We will put okay. Okay. After this, as you can see, there are multiple options for designs. As we saw in CST, in modeling section, we had different surfaces. See, similar to here, in HFSS, we have different surfaces. Okay, there are surfaces like this in which there is no thickness introduced or even present in there. So if I select this rectangle, for example, and if I put it here, in HFSS, if you want to make any structure, you simply select any options from here. Okay, you click on the axis, okay, and then you can extend however you like. After extending, you can click again, and then you have a structure. After this structure is created, there's a dialog box that you can clearly see. Okay, as you can clearly see, okay, as you can clearly see in this dialog box, you can only see the x-axis and the y-size, x size and y size, and you can see the position. In this structure, there is no height mentioned or there is no thickness introduced for this particular structure. Okay, but when we are designing unit cells or FSS, we see that for every structure, every part of that unit cell, if we whether we take the ground or we take the substrate or we take the top layer, we have some thickness introduced to every single part of that unit cell. So we will not use this. Okay, we can simply click it or delete it. Okay, for now starting with the unit cell, we will simply first select this box. In the draw in this section, in draw section, we will simply select a box. Now after selecting this box, okay, as I said before, in order to make any structure on the HFSS, we will simply see that the black dot, you can see the diamond shape on the axis. You can put it anywhere if you like. Okay, in order to start making this structure or creating this structure, first I will click on it. Okay, after that, the HFSS is telling me to expand this structure. I will simply expand this structure however I like. Okay, then this is currently telling me to do in the X or Y axis. So you can see this is right now in 2 dimension. Okay, after I click again, now it will tell me to increase its height. The height I can go however I like, but we will be able to change or modify the coordinates as we want later, as you can see in a few seconds. So after I just randomly click on its height, now the dialog box appears. Now, if you compare this to the previous dialog box that we saw, there was no Z size mentioned in the previous dialog box, but there is Z size mentioned in this dialog box, which means that this particular structure can go in all dimensions. So those structures that we previously saw were in 2D, this structure is in 3 dimensions. Okay. Now, the coordinate system in ANSYS HFSS compared to CST is very different, and we have to understand the difference very clearly in order to make any unit cell or any type of structure, any FSS. Okay, so for position, first of all, so position in this position is basically your start point. Position is basically the base from which the structure is started. Okay, so I can simply put, let's say, I put minus of L by 2 as its x coordinate. I put a comma, then I put minus of L by 2 again as its y coordinate, and then I put 0. 0 as in if I want to start the structure from the ground. Okay, so I'm taking z equals to 0 at my starting position. Okay, then this is selected. After I click enter, it is asking me to simply give the value of L. So that I can write 10 micrometers. So I can just simply write or you can say, if I'm not writing you can expand this unit section, okay, and check here as well. I can write so it will give me micrometers. I will put okay. Then I can go in my X size and my Y size. Now, the X size is Y size compared to in CST. If you remember, we simply did minus L by 2 to plus L by 2. That you cannot do in SFSS. Okay, the position is your starting point, and X size is Y size is where you're supposed to end the structure. That X size is Y size is simply telling you the exact parameter or the exact length and width of that particular cell. So, for example, if I put X size as L, select it, and then Y size also as L, that means that my unit cell will start from minus L by 2 on the coordinate axis, and its complete size is L. So it will first go from minus L by 2 to 0, and then 0 to L by 2 automatically. So in this, if I were to put L by 2 in X size, this structure would be stopped at 0 itself. We can check that clearly if you want to, but for before that, we can set that Z size. Okay, so we said that the position is 0. We start making the ground from 0, taking it z equals to 0 as our base, and then we will give the height to this ground. So for height, I can just simply say that tg, I can say this is the thickness of the ground. Okay, now it will ask me. So for ground thickness, I can say this is 0.035 or something. Okay, I simply said okay, and then I will say okay. So now this gave me something. Now I cannot see my structure. So in HFSS, if you simply want to see your structure completely, you can either go here towards your screen, all beside all these structures, you can see fit all. Okay, so you can click on fit all and your structure will be seen clearly. Okay, or there is a shortcut, you can simply do Control D in order to see your structure completely in frame. Okay, and if you are confused that why it's not symmetric or anything, you can simply navigate yourself to orient. You can extend this orient option and see top view. After this, you come to simply do fit all or Control D, and you can see that this is completely symmetric. This is a square patch. Okay, after this square patch, now as I told you, why we picked L or L here, not L minus L by 2 to L by 2 as we did in CST. Now, if I were to do this L by 2 or L by 2, you will check. You will simply see that the structure stopped at the origin itself. It's not even a complete structure. Okay, if I were to measure this side, this length or width, this will not be L. Okay, this simply started from L by 2 and it ended at 0 because this point in HFSS is our origin. Okay, so in order for it to completely extend to the L length and width, you will have to put L here. So we will say L and then L. and okay. Now we have this structure. Okay, now we make our ground as metal, like we assign our ground plane as metal. So we want that to, like we have to do that. So first we will select this box one. Right now you can see this box one is coming under the vacuum section. In HFSS, if you make any kind of 3D structure, it automatically goes under the vacuum material, but we can change it very easily. We'll first double click on this box one and we can change its name. So we can say this is the ground. Okay, now we can change its material. Now this option from material, it's giving me option like to edit or put it vacuum. It has yet not stored any type of material that we can assign it. So we'll just go to edit. Okay, and then we can search whatever metal we want to assign to this particular box or this particular ground. Okay, so we can, for example, search gold. So I have gold here. Okay, now this gold we can just select and then we can put okay. After that, we can now in HFSS, if you were to design every single box or any type of box, it automatically picks a color and that color stays default. So if we don't want ourselves to be confused with all those structures having exactly same colors, we can change it on our own. So the color we can pick for gold, we can pick this color, okay, and then we will simply put okay. And now we can go and you will see that we have gold here. Okay, you can also see this in orient shape. So we will see like this is our unit cell. Okay, now we have made the ground of this. Okay, now on ground we will make our substrate as we already know. So again I will pick this, select this box and I will make the substrate. Now there are a few tricks if you want to make the substrate. There is one easy way. Okay, at first I told you that if you want to make any box in HFSS, you can simply click like this, select it, okay, and give it height, expand it and then give it height, and then the dialog box appears. Okay, there's one another way if you want to do it and it will probably be easier for you. Okay, so we simply don't not need it. Okay, what we can do is select the box and go to the edge of the ground itself, because as we know, the ground and substrate are of same sizes in dimension wise. In x and y axis, we know that ground and substrate are of same sizes. So we can simply put the box in here. You can click here and then expand it to the size of the ground like this. Okay, and then we'll extend the size simply like this. Okay, by doing this, we basically have our substrate, okay, without the need of specifically assigning any type of position in this. Okay, we simply know that this it started from this point. Okay, and now we can basically give this substrate different height or variable if we want to. Okay, so now if you very clearly notice, this position is again very important. This position is important for one reason, and now that is the z coordinate of this position. This z coordinate is 0.035. As we said that 0.035 is our TG or ground point. Okay, so it immediately knows that the substrate is on the ground and it is starting from TZ only. So our initial coordinate for the z-axis is TJ itself, and then the substrate will be mounted on that ground. So it will start from TG and it will go to the height of the substrate itself. Okay, so instead of 10 and 10, we can simply say that this is L and L. Okay, and for Z size, okay, we can simply say that let's suppose it is TS. Okay, TS, we can signify that this is substrate thickness. I simply put enter and now it is asking me the thickness of the substrate. I can say maybe it is like 3 micrometers. I'm taking random value, so this is like 3 micrometers. I put okay and then okay. So the substrate is made. Now again, the substrate needs a material to be assigned. So we will double click on the box one. We will name it substrate. Okay, and then we can change the material. For substrate, we need dielectric materials. So we can take any, for example, let's say polyamide. Polyamide I can take, it is loaded. Now I'll put okay. And then I can change the color just to not get confused for later structures. I can make it white. Okay, and then I put okay. Now the polyamide is made. Now if I want to again see the entire structure in frame without any issues, I simply do Control D or fit all. That I can do. Now this is our ground and then substrate. Now what we make on the substrate on the top layer, whatever we mount on that top layer, that can be of anything. Okay, that structure can have endless possibilities. You can make any structure of any kind. We can make squares, we can make like rectangles, we can make circles, triangles, octagons, hexagons, whatever you like. And there are multiple operations that you can also do. So in this first section, we will just understand what kind of operations we can do and how we assign all these variables or positions or heights of whatever the structure we want to design on this substrate that will be mounted on this substrate. So if I were to take, let's say, like a square, okay, so I take a box again, okay, and let's say if I want to make it like this, I will again expand this and then give it a height. Okay, now let's see again the positions of this. So for example, if I were to say that this is my upper region, is my patch or something, I'll say this for, though I can say it is from minus PL by 2, I can put this coordinate, okay, for both X and Y axis, I can say this is minus PL by 2, okay, and then now this is the important part, the height, the starting position of this resonating layers or the resonator that we are putting on the substrate. Okay, the starting point for this will be the ground height plus the substrate height. Okay, we are starting from the substrate top point. Okay, and then it will go to the height of the resonator, whatever height we will give this particular box. So we have to first start from TG plus TS. Like I'm starting the structure from the substrate. So it will start from first the ground height, then the substrate height, and then we will give a height whatever we want to give this height. So first of all, PL we can give any directions for now. We are just learning the operations. So I say let's 8 micrometers I give this patch. Okay, now the full size will be again PL, not just L by 2, it will be PL, otherwise it will stay and the origin itself. So PL. Now enter this. Now the Z size. Now this Z size again can be different from the ground or it can be as equal from the ground itself. Okay, for right now we can say this is TM. Simply if I were to say that this layers thickness was equal to the ground, I could have just simply put TG here. But there are surfaces or there are models in which there is a significant gap or significant difference between the values of ground and the resonating layer on top of the substrate. So I can simply put TM in order if I were to change this later for optimization purposes. So I can simply put TM and whatever a value I want to put, I can say let's just 0.1 micrometer this TM is. Okay, and I put okay. So this again, this structure or this square that is on the substrate is not having any material. So we will again name it a material. So for example, if I were to just say that this is square, okay, and I will change this material to gold, and I change this color to this, and I'll say okay. Now you can say that the structure, you can very clearly see that the structure is here. Okay, you can see the top view of this. You can again do fit all to see the structure very clearly. Okay, now what are the things that we can do within this structure, within this square? Okay, the possibilities are endless. We can do whatever we want to do with this structure, but within the range of this structure. Now within the range of this structure, by that I mean, like if I were to subtract something from this or if I were to unite something from this, okay, then it should be limited to this structure only. The dimensions were to be limited with the structure or limited to the substrate. Okay, so for example, if I want to cut something from this or subtract something from this or add something from this, we can do that or learn that. For example, we have all these operations. So if I were to select this square, you can see that all these operations are now highlighted as the structure of the square is highlighted. We have move, rotate, mirror, a long line, around axis, or through mirror. These are, you can say, primary or something expressions. You can see that move, rotate, or mirror this particular structure. For example, if I were to move this, okay, I can simply put on move. Okay, so this square can be moved now. How we can move it? We will simply click on its center. You can see if I navigate my cursor to the center of this square, it will show a circle. Then I can click on it. After clicking on it, I can move this structure however I like. Like this I'm by moving this square, you can see that this diamond shape, I'm moving my cursor, it is being moved. It is basically moving the center of that square, so I can move it wherever I like. So let's say if I shifted it towards the right side a little bit, okay, and you can see that is shifted. It is shifted by this vector. Now this vector shows the amount that is shifted. So it was originally on 0 0 0. We know that it was originally on the origin. Okay, now this is shifted 0.5 in the y-axis, but it is also shifted a little bit on the z-axis. We will simply put it 0. Okay, then we put okay. Now this structure, as you can see from the previous step, that it is slightly shifted towards the right. Okay, this is how move works as an operation. What we can also do is that after moving the structure, you can see that there is a move operation right below the square. Okay, so we can modify the coordinates of this square's movement however we like, in whatever form we like. For example, if this is 0 0.50 right now, I can simply put 0.5 in x-axis again and say okay. So it moved in both x and y-axis itself. It did not move in the z-axis, as you can clearly see by rotating the structure. Okay, it is still very much grounded on the substrate. Okay, now we can do fit all and top. Okay, now this I have. So we simply did move right now. Okay, now I can select the square and we can go through the other things as well. Now is the rotate option. So the rotate operation, I will simply select the structure and then I'll do rotate. Okay, now it is asking me to rotate the structure in a particular axis. Okay, it can be in x-axis, it can be in y-axis, it can be in z-axis, whichever axis we like. Okay, so if I were to, let's say, rotate this in the z-axis, and let's say if I'm rotating this by like 10 degrees or something, I rotate this by 10 degrees, I will put okay. So it is rotated in the z direction, not x or y direction. Okay, it is rotated in the z direction itself. Angle is 10 and I will put okay. Now as you can see, it is slightly out of the unit cell, slightly out of the substrate. So this means that the movement we did, okay, it can be wrong or something. So you can put simply 0. So in order to shift this back to the center, you can start the movement a little, you can shift it however you like, in a way that it comes back to the unit cell, or it comes back mounted on the substrate completely and not leaving the structure. Right now we rotated it by 30 degree, but as you can see, similar to move operation, the rotate operation also comes below the square. Okay, so in rotation you can also see if it's 10 degree, we can do 20. Okay, we can simply see what this does by applying this 25 or 30. Let's see if we do 30, we do apply, and this is how it works. Right now we'll just let it be at 0. Okay, we saw move and we saw rotate of the structure. Both things we saw. Okay, now if we want to cut something from this, or we apply basic Boolean operations on this particular structure. Now for Boolean operations, we have unite, substrate, intersect, and things. Okay, we will simply start with having a shape. We can create a shape for that. Let's just select any box. Let's select a box and make it like this. We make a box again. I'm first expanding, then I'm giving it a height. Okay, now I can give it whatever dimension I can want. For example, I first made it p, so let's do it minus p by 2. Okay, comma minus p by 2, and again I want ts plus tg as my starting point from subscript. Okay, now it's asking me p. I can simply give any dimension, for example, but it should be less than 10 because your unit cell size right now is 10. Your substrate size is 10, so it should not exceed the size of the substrate. So I can simply put it as 9 or 9.5. Okay, micrometer. So I should put u1 and enter. Now I can say that this is p on x size, p on y size, and z size I will simply put again as tm, because I want to have both of my structures which I was supposed to add or subtract on the same size or on the same height. Okay, both of those structures are of the same material and both of those structures should be from the same height if I were to do any kind of Boolean operation on those structures. So if I put this, I will simply do okay. Now you can see there are two structures in here. We will again, as this is box 1, we will say that this can be square 2. Okay, and we will assign it gold, again the same things that we did previously for that model. Okay, and we put okay. Now you can clearly see from the top view, if we see that there are two squares. One is this square that you can see that we just made, square 1, this one square, and then square 2. Now these two squares are clearly visible, but we can also see that these two squares are intersecting right now. They're overlapping on each other, so we can actually perform some sort of Boolean expressions on this. So if I were to say, if I were to say I had to perform some Boolean operations on them, I will select both of them by like pressing Control, and then I will select both of them. I will select both of them, then I can apply any of these Boolean operations on this. If I were to say I click on unite, then you can clearly see then these two structures are united. These two structures are added. There are no extra lines that you can see that these two structures are not separate. You can see that these structures are united completely. Okay. Now, if I were to not unite these structures, I were to delete this operation. So I can simply either delete this unite from here. Okay. And these structures will go in the unassigned section. Okay. This simply go to the unassigned section. So I can give it back gold and I put okay. Now I want to do some different kind of operation on these two boxes. I don't want them to unite. Okay, so what I can do is I again press Control and select both of these structures, and then I will do, let's say I will do subtract. Now this subtract dialog box, you can very clearly see this subtract dialog box is like I have the left part. In left part is this, left part is basically my base structure, and the right part is what I want to subtract it from. So if I were to say the square 2 is my bigger square, right? Square 2 is my bigger square, so I will say square 2 should go there. So what I did is that what I want to subtract as in the base model, I simply put on the left side, and what I want to be subtracted, I put on the right side. Okay, now square 2 is my bigger square and square 1 is the smaller one. Okay, now we have clearance for that. I can simply put okay. Now you can very clearly see that the smaller square has been edged away from the bigger square. This is how we do our rotation. This is how we do our, subtraction of operation. Okay, so we studied unite and subtraction by simply this. Now there are multiple shapes you can think of. We were just dealing right now with boxes. We can also deal with this or cylinder shapes or whatever. Let's start with this. Okay, this is basically our polygon structure. Okay, so let's first orient it. So designing this polygon structure again is very similar to how we design box. So we'll select this polyhedron structure. We'll again click it, and then click it. Box is asking us for the number of segments that we can give to this particular polyhedron. Okay, so if I were to say I want a hexagon, so I will just simply put 6 here, and I will say okay. Now the dialog box appears. Okay, after this, now the dialog box appears, and I can particularly assign whatever values I want for this hexagon. Okay, so for example, it is first asking me the center position of this hexagon. Okay, now if you relate this or compare this with CST, in CST also you have center, in CST also you have this, instead of start position you have your Y max, Y min or Y max. Okay, this is the difference between CST and HFSS. You have a starting position in HFSS and the center position in polygons. So in center position, I simply will say that my center is origin, as everything we have been doing taking origin as our center. Now starting position, we can say that the radius, we can say this minus r by 2. We can say that the radius of this hexagon is r. Okay, so we can say that minus r by 2 comma minus r by 2, and then again we want this to be mounted on the substrate, so we will say this is starting from tg plus ts. Now the height of this tg, okay, okay, there is some error which is showing while passing expression minus r by 2 as error is not because the character 2r is not defined as new variable in the context. Okay. Okay, we can simply put as at L for start. Okay, how it is doing. Okay, and we can give the height as again Tm. Okay, number of segments we already decided that it was will do. Okay, now as you can see, there is a problem with the height. Very clearly, there is a problem with the height of this regular polyhedron. It is starting from, as you can see, 0. Okay, for that we have to actually put the center position to something. So we have to put this center position plus ts. If I were to apply this, so it immediately now it's coming on the surface. Okay, we can put it as you can see in the top view, and we can do Control T. Now, as you can very clearly see that this is very much exceeding the limit of the substrate, because it is exceeding the height and all that. The radius is very much larger than 10 micrometers. Okay, so we can change it simply by, we can see, let's say it is instead of L by 2, I can say it is L by 4, and then I put OK. Now we can see that the hexagon is very much confined in the on the substrate. It is not going outside of the unit cell. Okay, now simply as we did in the box, if we were to make any kind of polyhedron, and by default it goes into vacuum and it has a different color. Okay, so we'll again assign it as gold. We can name it as let's say hexagon. Okay, and we will assign it a color, and we'll do okay. Now we can clearly see that this is on the substrate, and again we have this issue that this hexagon is kind of overlapping with the structure we previously had. So again, we can think of operations that we can probably do on these two structures. We again fit all, okay, and then we can select maybe these structures. We can select hexagon and this square too. Now we can also unite this. We can subtract it, but right now we can do unite. But right also you can do what also you can do. We can play with the hexagons, the rotation angle as well. So if I were to say, let's say this is the hexagon, and if I rotate it by let's say 30 degrees in the z-axis, if I rotate this, this is like this. So again, I can play with the rotation angle however I like. Okay, and it is on the structure. Again, I can simply put, I can unite these structures. We select square 2 and we select this hexagon, and again we can access through a lot of operations. We can simply say unite. Again, now we can understand a few more things about this. We can understand a few more operations. Okay, so let's say we add something. Okay, we add something and then we understand how other operations work. So if I were to say, we are in orient shape. Okay, I make this random structure or a slit, whatever box type. I'm giving it some height. Okay, whatever the dimensions are, we are simply understanding right now the operations. Okay, so we can give the height as it is starting from TS plus TG. Okay, and the height goes to TM as we did for all those structures. So we simply do okay. Let's see. With the height. Let's redesign this box. Okay, we made this box. From that point only, okay, we can give the size to TM. Okay, now we can okay. Okay, the dimensions are shifted. Let's shift it back to okay. Now this is here. We can move this simply back to wherever we want it. Okay, we can apply the structure on this, operation on this. So we can select this, we move it, we select on this, we go to the circle, we click on it, and then we can put it back on the substrate itself. Okay, so we were initially on some structure. Now we can see this is right now on TS plus TG and okay. Now if I see in orient direction, you can clearly see that this structure is now on the substrate. Okay, now again, I will say box one. I will let's say this is, I will name this as a slit. Okay, and I will assign material as gold. I change this color. Okay, and now we have this slit. Now we can clearly see in top view that we have this slit on the substrate, and we can now think of assigning some operations or mirror operations on this structure. Okay, so what we can do, if we can select this slit, it is giving us the option of mirror. Okay, so we can mirror this. Okay, we can simply do select this again from the from the center. It's showing this, and we can mirror it, let's say right here. Okay, it is showing us a dialog box that it is shifted to this particular point. Okay, we want this height to be TS plus TG plus TM. Okay, and we do apply or okay. Let's see, there is some issue. So the base position was this. We had the base, when we see the mirror operation, it is showing us two options. First, we have the base position. Okay, then we have the normal position in which this is being shifted to. Okay, or you can see, we can simply do what, select this slit and we do through mirror. By through mirror, we can see that in through mirror we can rotate this however we like. For example, if the through mirror is put on this particular structure, and we can rotate it to create a mirror image of this itself on the structure. We can rotate it however we like. Okay, for example, if I were to say this is here, okay, and this is how it is done. So we'll put okay. Now you can see that there are two duplicate mirrors, two mirror structure of this. So we have made a mirror of this slit by keeping this straight line or this axis basically as its reference, and then we basically mirrored it in this direction. Okay, you can either do this to create a plus shape or whatever you like, or you can simply rotate this, make a copy of this and rotate. Okay, we can also do is that we select this Okay, we can simply do Control C and Control V on this on this thing as well, and it will create us a copy of this particular slit. So we will do Control C and then we will do Control V. So it shows us that there is a slit again of the same type. We have this slit and then we have this slit. These are the same slits, so we can move this however we like. We can rotate this however we like. For example, if I say that if I were to move this or rotate this, so I select this and then I rotate it in the Z axis, and I will say this is, I rotated this in 45 degrees, and I said okay. Now you can see that this particular slit is rotated in 45 degrees. Okay, and if I were to rotate this, you can see that this slit is rotated in 45 degrees and it is adjusted right here. Okay, and again, as you can see that these lines are intersecting. These structures are, these slits are very much intersecting with each other. So you can select these slits again. These two slits, as you can see, are intersecting with each other. So you can select these slits. Okay, and you can use unite or substrate or whatever you like. Okay, so we saw that we can unite these structures like this. Okay, if I don't want to unite this structure, again, as I said in previous way, we can simply click on the unite operation and we can delete it. Now these structures will separate itself again very clearly. Now, if I were to set, let's say, again operate on these particular slits, I will simply select these two particular slits. Okay, sorry, this slit again, and I can say this slit. Okay. Okay, this because I deleted the unite operation, you can see that the previous slit that we did any kind of operation not, it went into the not assigned section. Now, if again we have to remember this very clearly, if we perform any kind of operation and we want to delete this, if I were to delete that particular operation from this navigation tree, okay, whatever we deleted or whatever we united will go into not assigned section. So we will again have to assign it some sort of material, because you can see this material is not assigned. So we'll again assign it gold. Okay, now we can see this is again clearly in the navigation tree below the gold structures. Okay, now again we can, if I want to operate it, we can operate subtract subtraction operation on this. Okay, so we select subtract, and now we want to remove the slit one, this slit, because this is very clearly exceeding the unit cell or the substrate dimension. We want this to be removed. So we will put the left side for the structure that we want in this, like we want to subtract from, and this slit one will be the structure that will be subtracted. Okay, and then I will do okay, and this structure is subtracted. Now there is one more thing that we can do. Then if you see, there was a dialog box. Now we will simply assign this material again. Let's just check on this again. So if I were to select these two, okay, and I say subtract, okay, you can see this this tick mark. This says clone tool objects before operation. What this does is that it does the operation exactly as it is. It will subtract the slit one from slit, but while subtracting it, it will create a clone of the slit one if we were to use this again on a different operation. Okay, so if I check this tick box, I'll do okay, it will subtract, but that slit one will still stay in that structure if I were to perform any type of operation on the slit one again during our analysis or during any other optimization or during making any different type of shapes. Okay, all we can do is to click that box. If I were to have this structure of this, if or this particular structure is needed anywhere later in optimization or designing, I simply will click on that clone tick box. But if we don't need it, we can again delete the subtraction operation. We can also delete this clone operation. Okay, and we will simply select these two and subtract it without cloning, because we actually do not need that. If we do not need that, we don't have to clone it again. So you can see that all these structures we understood rotation and okay, now will be the validity session. So we will have a 15 minutes break on the hands-on session. Okay, over to you, Swati.
Hello. Sir, may we start the validity session?
Yeah, we can start.
Okay. So good evening all the faculties, organizing team and the participants. I, Swati Gaur, research scholar from Department of Electronics and Communication Engineering, MNIT Jaipur, welcome you all to the validity session of the FDP on recent trends in frequency selective surfaces for 5G and 6G applications, held from 3rd October to 14th October 2025. To proceed further, we are having now Dr. Reena Kumari ma'am, the FDP organizing member. I request the organizing coordinator of the FDP, Dr. Reena Kumari ma'am, to kindly share the insights of this FDP with us and the valuable feedback from your side, ma'am. Please, over to you, ma'am.
Okay, thank you, Swati. Good afternoon, one and all. As we come to the conclusion of this enriching faculty development program on recent trends in frequency selective surfaces for 5G and 6G applications, organized by the Electronics and ICT Academy MNIT Jaipur from 3rd October to 14th October 2025, it is my privilege to deliver the vote of thanks on the behalf of the EICT Academy MNIT Jaipur and FDP Organizing Committee. I extend my heartfelt gratitude to everyone who contributed to this intensive 40-hour online FDP program. We are deeply thankful to the leadership of EICT Academy, including the Chairman and Director MNIT Jaipur, Professor Narayan Prasad Padi, Chief Investigator Professor Vineet Sahola Sir, Coordinator EICT Academy Dr. Satya Sai Jagannath Nanda Sir, and Co-Chief Investigator who support and ensure the program aligned with the vision of Meet Y and the objectives of Make in India and Digital India. So this was an intensive 40-hour training program structured to provide a comprehensive learning experience with 20 hours of expert talk and 20 hours of practical hands-on sessions. Our sincere appreciation goes to all these esteemed experts and speakers from reputed institutes like enterprises for sharing their profound insights on topics ranging from metamaterials and frequency selective surfaces for 5G and 6G to AI ML assisted design and intelligent reflecting surfaces. So if you will see about the FDP, total number of distinct speakers are available 18 and FDP hours 40 hours, expert lectures 24 hours, hands-on session 16 hours. So we have discussed about program modules also. From module 1, like fundamental of electromagnetic band gap materials, it is coming like metamaterials, meta surfaces. And module 2 also, it is based on your beam forming and MIMO support, band pass and FSS designs. And module 3, you can see terahertz FSS design challenges, reconfigurable tunable FSS using MEMS, graphene, liquid crystal. Under module 3 also ultra wideband and metamaterial, low profile flexible designs are there. Module 4, in module 4, AI/ML assisted FSS design, like manufacture your energy harvesting and wireless power transfer are also there. FSS for security and stealth communication system, nano electromagnetics, terahertz sensing and analysis, intelligent reflecting surfaces, reconfigurable intelligent surfaces, and reabsorbers, polarization converters are also there, millimeter wave terahertz imaging for biomedical application. Module 5, simulation-based design like metamaterials, frequency selective surfaces, observers, polarization converters. And your participants are total number of registrations 53 and MNIT participants are 7, other institutes 46. And some criteria for award of certificates we are also doing. So assignment of submission, excellent, very good, good, fair and satisfactory are also there. So I would also like to thank my fellow program coordinator, Dr. Sarthak Singhal, organizing committee and technical team for their meticulous planning and flawless execution of each session. A special thanks to all our participants whose active engagement and enthusiasm made this FDP vibrant and successful. As we are approaching to closure of this FDP, let us carry forward the knowledge and inspiration gained during this session and continue contributing to innovation and excellence in the field of 5G and 6G communication. Thank you everyone for being part of this wonderful journey. Have a pleasant evening ahead. And these are some glimpses of FDP you can see. And thank you all. Thank you so much, all of you.
Thank you so much, ma'am. May I now request the Chief Investigator EICT Academy, MNIT Jaipur, Dr. Vineet Saula sir, to kindly share a few words with us on this FGP.
Yeah, good afternoon. I think I am audible.
Yes, sir, you are
Yes,
audible.
sir.
I think I should thank Dr. Sarthak and Dr. Reena Kumari for putting a lot of hard work in planning this program and making it successful in all the sense there. I hope all the participants will benefited from this program, and you can look forward to such programs next coming months and the next year, financial year that way. I would like to thank all the speakers who have been invited and have devoted their time for our programs, talk delivery and so on. And thanks to Professor N.P. Padi Sahab, our director, for his constant support for such kind of activities. And I think Professor Nanda is here to tell you more about EICT Academy and other programs. So I take rest here and then wish all the best to all the participants. Thank you, Rita, and thank you, Sarthak, again. Thank you very much.
Thank you, sir. Thank you
Thank
for
you,
your
sir.
support.
Thank you very much, sir. We are honored to have Dr. S.J. Nanda, sir, the coordinator EICT Academy, MNIT Jaipur with us. I request Dr. S.J. Nanda, sir, to kindly share a few words with us, sir.
So I congratulate all the participants of this workshop, as well as the coordinator, Dr. Sarthak and Dr. Reena, for putting up a lot of effort to organize this particular event, especially calling a lot of speakers from various IITs and NITs and other reputed institutions which have brought the quality of this particular FDP. As Professor Binit Saula sir has mentioned, there are a lot of FDPs which are streamlined in the upcoming months, especially November, December, and January. This is one of the course on recent trends in 5G selective surfaces, which we have witnessed for the 5G and 6G application. There is another upcoming course in the November, which you can also look at on the 5G, 6G wireless communication, which is streamlined from November 24th onwards. So those those participants who will be interested in the 5G, 6G communication and its advancement, they can also join that particular course, which is floating in our MNIT website. Obviously, the certification on this particular program will be very much helpful for all the participants who have joined and given quiz, and that will give a progress to their achievement. Uh, with the EICT Academy from in the first phase, especially from 2015 to 2023, our academy has our academy especially completed large number of participants training in the first phase, and with the second phase from Ministry of Electronics and IT from 2024 onwards, for last 2 years we have been doing it for the researchers and for the academician throughout the country. And over the time, the courses are getting popularized. As you can observe that large number of participants throughout the country have joined this particular program as well as the other programs. So I expect all the participants to look forward others similar kind of courses and join for their benefit. So thank you everyone. That much from my side. Thanks.
Thank you, sir. Thank you very much. Participants, please raise your hand if you have, if you want to share your feedback for this FDP. Any participant, if they want to share their feedback, then raise your hand. I just want to share something. This FSS based FDP has been a truly enriching and beneficial experience for all of us. All these sessions were highly interesting, especially the hands-on training and the active participation from attendees through their insightful questions and queries. As both an organizer and a participant, I have learned a lot from the expert and discussion throughout the program. I sincerely thank all the speakers, participants, and all the other organizers for making this FDP a great success. Over to you, Swati ma'am.
One participant has said that it is a great opportunity for the people, those are struggling to start. Thank you very much, ma'am. Thank you so much for your valuable feedback. On behalf of EICT Academy and on behalf of Electronics Department, is
One participant wants to
Yes.
share. Yeah, Abhishek, kindly you can unmute yourself and share your feedback.
Thank you, sir. I'm Abhishek Karwa, PhD scholar from BITS Pilani. Actually, I'm also pursuing my PhD on the topic of frequency selective surfaces. That's why I joined this course, and really, I'm amazed to say that this course was designed so well. Even on the Canvas platform, we have find the complete syllabus. that what we will be taught, and I'm 100% sure that all the topics that are written on that syllabus are completely delivered to all the participants. And even I can say that the tools which were taught by Vikram sir and Sarthak sir, I'm very thankful to both of them. Sarthak sir, I read your papers seriously, because I am also doing the same task, absorber, and even I discussed with my supervisor also that Sir Vikram sir and Sarthak sir are having the papers on terahertz. So my supervisor also insists me to read those papers continuously and get learned from them also. And even the speaker from IIT Indore, Professor Dr. Saptrishi Ghosh, I really enjoyed that lecture. How, because I was struggling in how to draw the ECM of any FSS circuit. So I really got to know how to draw the ECM, and even one of my paper is just I'm struggling for that how to draw ECM. And yesterday night I completed that ECM and I got exact result which I was getting in ADS. Uh, so I thank you. I once again thank you from the bottom of my heart to all the organizers and even the management team who is very prompt to answer my queries and the problems and regarding the technical glitches. So once again, I congratulate to all the team. Thank you from the bottom of my heart. Thank you, sir.
Thank you, Abhishek, for your feedback. Any other feedbacks from any participant? Okay, Swati, now we can proceed with. Okay.
Thank you very much, sir. Thank you. I share my deep gratitude to Professor Vineet Saula, sir, Dr. S. J. Nanda, sir, and all the organizing coordinators for this FDP. Thanks a lot, sir. I
Yeah,
think we
thank you,
can
Swati.
conclude with the validatory
Thanks.
session.
Thanks, Arthur. Thanks, Nanda.
Thank you,
All the
sir.
best to
Thank
all participants.
Thank you, sir.
Thank you,
Thank
sir.
you.
Thank you so
Thank you.
much.
you.
Dear participants, we can now conclude the validatory session here, and the hands-on session will be continue now till 5:30. You are requested to kindly stay connected with us. Sorry to interrupt you here. We are going to have a group photograph. Hello.
Yes, ma'am. Yes, ma'am. You are
Sir,
audible.
are you audible, sir?
Yes.
All the participants are requested to kindly turn on the camera, and even the coordinators, FTP coordinators are requested. All the participants, please turn off the camera for the small group photograph. Thank you. Vikram sir, you can continue with the hands-on session.
Okay, ma'am. Okay. Invisible?
Yes, sir.
Yes.
Yeah. Okay, sir.
Okay, so up until this point, we have understood all the operations, and you can see the unit cell what that we have made right now. So I will leave this structure for 2 minutes as it is. If you have any doubt regarding the operations that we performed on this unit cell, you can leave the questions in the chat box. Okay, I will wait for 2 minutes for all the questions if there are any queries. Otherwise, we continue with the a unit cell that we will create from scratch again after this. If there are any doubts, we will solve them. Otherwise, we will simply start with the unit cell.
We can continue with the further sessions.
Okay, sir. So we can simply start. Okay. Previous okay. Okay. Now we will start designing the unit cell which we were supposed to simulate. Okay. We will again simply start as we did with the previous unit cell design. We will go in first HMSL's solution type and we will click on model. Model selection option. We will not be able to assign the Flowquate port on this unit cell. Okay. So we will do model and then we will click OK. And again, we will go in modular. We will go to units and we will assign the units to micrometer and we will rescale to no units. Okay. Now we will make all the entire unit cell from scratch. So we will make first the ground, then we will make the substrate, and after that we will make the top layer. Okay. So we will start again from the ground. We will select draw box. Okay. And we will simply first click it then expand it, and then height, and now the dialog box appears. Okay, so we are keeping, for this designing, we are keeping origin as the unit cell center. So the positions I can simply say is again minus L by 2, comma, minus L by 2, comma, we are starting the ground from 0. Okay, now okay. Now it's asking me for the parameters. We'll say L, my L is 10 micrometers. So I'll say 10 micrometers. Okay, and I'll add in X and Y size as we discussed in the previous hands-on session. In X, I will put L, I will enter. In Y, I will put again L, I will enter. And in Z, this time around, I will put again T, G as the ground's thickness. And I will again put enter. Now the dialog box appears and I can simply assign TG a value. I will put 0.035 micrometer as the value for this ground. Okay, so I simply put OK, and then the structure is visible. For again the structure to be in frame, I will do fit all or Control D. Now, as I said before in the session, the default box, if it's created, it goes under the vacuum section. So I will double click on it for it to assign any metal or any other material. Okay, we will simply say this box one is ground, and we'll go into material. In material, we'll go in edit. Okay, and we will search gold as the material. We'll search gold, and then we will do OK. We'll assign it a color, and we'll do OK. Now we can clearly see that the gold ground is visible on the HFSS interface. Now, this after the ground is made, we will make our substrate. Okay, so we can again select the box. Okay, and as I said, there are two ways of making substrate or any other box. Okay, you can simply either put it anywhere you like on the surface. So I will simply do it like this and expand this and then give this a height. And after that, I will again assign my variables. The coordinates again will be minus L by 2, comma, minus L by 2, comma. This time my starting point will be TG, because the substrate is being mounted on the ground. So TG will be my starting point. Okay, the X size will again be L. The Y size will again be also be L, and Z size will be the thickness of the substrate that we can assign as TS. Or any name or nomenclature can be completely arbitrary. You can pick however you like. So TS, I will simply say is 3 micrometers. Okay, and I'll put OK. Now, as we previously discussed, again we have to change and name this is my substrate. Okay, and I will assign it a dielectric material, let's say polyamide. I'll put OK, and I can assign it a color, let's say white. Okay, and then okay. So I now have my ground and I have my substrate on this. Okay, now I will make a structure on the top layer, which is my resonating layer. Okay, first I have my ground, then I have my substrate, and on substrate the resonating layer, like all the structures that participate in resonating some kind of frequency or any value of frequency, that will be mounted on this substrate. Okay, so first we will start with again making a box. We'll expand it and then give it a height, and then the dialog box appears. Okay, now this particular part is important to notice. First, we will assign, I'll say PL, so this is patch length, I can say. whatever I'm putting on the substrate or mounting on the substrate, I can say this is patch length, comma, PL by 2. Again, now my starting point is simply TG plus TS. I put enter. Now it's asking me for PL. Now I will put PL as 9.9 micrometer. This will be very important. We will discuss it when we closely observe the structure itself. Okay. I put OK. And then I will put again PL. Y size I will put PL. And Z I will simply put as TM, indicating the metal thickness that is on the substrate. And for this I will can put 0.035. Now this can be different from the ground thickness as well, so that in order to optimize this particular value later, I'm not assigning it the same variable, I'm just giving it a different variable, even though the values for both TG and TM are equal. I will simply put OK and OK. Now again I will assign it a material. I will simply say this is my square. I will go in material. I will assign it gold, all the things that we have done previously, and OK. Now you can clearly see there is a square on top of it. We can go in top view and we can see the square. Now if we zoom this particular structure very clearly, we can see that there is a gap. There is this very visible gap that you can see with the edge of the substrate and the edge of the square. Okay, this gap is very important because the square cannot exceed the length of the substrate, or it cannot be exactly the same size as the length of the substrate. So this square's length and width as a square, so basically the square side is 9.9 micrometer as and the substrate's dimension is 10 micrometer. So the 9.9 was important. We cannot simply put it 10. Okay, those parameters cannot be equal, or the square's parameter cannot exceed the size of the substrate. Okay, so this was very important. Now we control D, fit all. Now for this unit cell, I want to make a square ring. Now the square ring would be something like I have this bigger square. Okay, and from this very origin, this origin point, I can see I can say that I have a ring, square ring, which means I create another square of some dimension which is smaller than the square that I have created before, and I simply etch that square from the original square. By that I will have a square ring instead of a simple solid square. Okay, so now I want to make a square ring. So I will first orient it to see the structure very clearly. Now again I will select the box. Okay, and I will again randomly just expand it and then give it a little height. And now the position of this particular box or the second square is very important, because now we want to cut this equally from all the dimensions. We want this cut equally from x dimension and x direction, and we want it cut equally from y direction again. Okay, for that we have to assign the coordinates very carefully. I will assign this now. Let's say now my PL by 2 is very important because I want the ring to be cut from the square like a little bit after the edge. So if I were to say that the square ring is starting from minus PL by 2, okay, it is starting from minus PL by 2, and I want the square ring to be like, let's say the thickness of the square ring, let's say, is 1 micrometer. Okay, so I would for that, or to obtain that, I would want a smaller square that is exactly 1 micrometer smaller than the first square in all directions, basically in plus x as well, in minus x as well, in plus y and in minus y. Okay, so I will simply start by saying that simply start by this. So minus PL by 2, and I can simply type plus, let's say I can say C1, like the cuts dimension. Okay, so what this does, is basically whatever value I assign this C1, it will start from minus PL by 2, which is 4.95 plus something, plus a value. So it will start from that, and then it will go to the assigned value whenever I am assigning the X size. Okay, so I can say minus PL by 2 plus C1 in both X and Y coordinate. Okay, now the height will be exactly as we did for the previous structures. It will be TG plus TS. Okay, now it is asking me for C1. Now this C1 you will simply put at 1 micrometer, and I'll put okay. Now the size of X is what is important in this. Okay, now we have to understand one thing. See, that position is where we in the start I already mentioned that the position is the starting point of this structure. Okay, so this structure you can very clearly see in this evaluated value part is starting from minus 3.95, not from minus 4.95, which doubled is 9.9. Okay, so I want structure to start from minus 3.95 and stop before 9.9 basically. Okay, before 9.9 I want it to be stopped, but I want it to be stopped also 1 micrometer before 9.9. Okay, so what I can do here, I can simply do PL as the X size, okay, minus of twice of C1. Say twice of C1. What this will do is it is creating the size of this particular square to be PL minus 2C1 basically of 7.9. Okay, so we created a 9.9 square as our bigger square, and we want to cut 1 micrometer from both sides. Okay, so if we cut basically 1 micrometer and minus meters from both sides. Okay, so we want the size to be 7.9 micrometers. For that, as PL minus 2C1, and we can do the same thing in direction. So PL minus 2 times of C1. This is ensuring that we are basically making square is the size that we actually want. Okay, now the size will be similar. I will say it is, and then I will put okay. Now again I will simply assign this. This is my square cut. Okay, I will assign the material gold, and I will so make it visibly not confusing enough for you, visibly very clear. Now if I see the top view, I can very clearly see that these two structures are overlapping with each other. Okay, so in order to make a square ring, I will simply have to deduct the remove this square cut part from this square part. So we learned this in the previous session, that in order to perform any kind of operation on multiple structures, on 2 structures or 3 structures, I will simply select both of those structures by pressing Control. Okay, and then I will do whatever the operation I want to do. Okay, now I want the square cut to be subtracted from the square. Again, I will repeat that in the left section, in the left part of this subtract operation, I have the structure from which I want things to be subtracted from, and the tool parts is basically the structure that is being subtracted. Okay, so I will say okay. After this subtraction operation is completed, you can very clearly see that we have a square ring. We can orient this, and we can clearly see that it is a square ring of a certain height. Okay, we can see the ground very clearly, we can see substrate, and we can see the square ring that is created on the top layer. Okay, so this is basically a very simple unit cell that we have designed. Now, in order to understand, in order to observe the results of this particular unit cell, we have to assign it boundaries as we did as we did in CST as well. Okay, there are boundaries on this unit cell. Okay, for that, to assign any kind of boundary on this unit cell, we also, as we probably already know, for flocate port assignment, we need the boundaries to stay in Z direction. So in positive Z direction and negative Z direction, and we don't want that boundary to be in X or Y. Okay, so for assigning boundary, we can navigate through here. First, these shapes are there, then we can navigate through here. This is called create region. So we can click on that. Okay, now we have this dialog box. Okay, now if I were to make a region that is basically the same dimension in every single direction, in X, Y, and Z, in plus X, Y, basically I can simply have my tick on this pad all directions similarly, but I don't want the the region, or basically the box or the boundary box, to be in X, Y direction at all. So I want it to be in Z direction only. So I will say pad individual directions like this. Now it is giving me the option to assign the value of the box's dimension in all the directions in okay, right now it's giving me the option to set the dimension in percentage offset, but I don't want it. I will simply click on it and it is giving me the option of absolute offset. I will do absolute offset instead of percentage offset. I will select that for both positive Z direction and for for negative Z direction. I will say absolute offset. Okay, now I can simply say that the value for this box can be, let's say I put it as A in both. Okay, and I can put this as 20 micrometers. I will put okay, and again I can put A here. Okay, and then I put okay. Now you can clearly see I do fit all. Okay, that this particular region is very clearly visible on the unit cell, and only in the Z direction. We can see that none of this region or box is visible in the X direction or in the Y direction. This region is only visible on the Z direction. This particular region in CST is already there, but in HFSS, we have to create this region in order to assign boundaries and excitation on this unit cell. And again, all this so that we can basically operate and receive some S parameters or results of this particular unit cell. Okay, again, we can also see that we have to understand one thing as well. Okay, the size of this region, for example, we simply took a random value. We took a random value as 20 micrometer, as you can see the region. We took a simply 20 micrometer as value. But if we are operating on actual unit cell, this size is actually in the order of lambda by 4. Okay, okay, in which lambda, it corresponds to the resonating frequency of any particular peak. So if we have any idea, okay, you can correspond the size of this region to lambda by 4. Okay, it is creating a box region, and now we will be able to assign boundaries and the excitation on this particular region. And after assigning those boundaries, we will be able to observe the results for this unit cell. Okay, we will 2 minutes, 2 to 3 minutes. After that, we
Okay, I think till this point, everything is clear. How we can create this, how can we design our structure, and how this boundary box we can design. Okay. Now, next, our next target is to define the boundary condition. As like in CST, we directly assign the unit cell boundary condition, and we can also check tick the ET0 terms and HT0 terms in the X and Y axis, so that we can assign our boundary along the X and Y axis. Because we are only targeting for this unit cell, that's why we have to assign the boundary condition along the X and Y axis. And after that, we have to assign our fluctuate port along this Z axis. Okay. In the CST, it will directly applied in the X axis and Y axis, ET0 and HT0 terms, or we can make a unit cell array, or in the Z axis, there is a open add space option, and it will directly choose the distance between your port and your design. But here we have to define the boundary condition. We have to make this boundary. We have to make it as a box, and then we have to make these surfaces. Okay, this boundary and this Z max. This is my Z min. Two options. One option is you can directly choose this box, and you can make a auto lattice pair. This boundary condition is called as a master slave boundary conditions in HFSS. In many of papers you have seen in the HFSS, when we are talking about the unit cell structure, then the master slave boundary conditions are applied for this simulation. So what is this master slave boundary condition, that we will see. Okay, so just okay, just tick this reason. This is my boundary box. Okay, right tick here. Okay, now see, there is multiple options. One is this assign boundary, then assign excitation. So for this reason, this boundary reason, we have to assign the assign boundary. So this method is direct method. I am directly applying the, okay, this assign boundary. In this, go to the coupled, because the opposite directions are coupled with each other. If your x min term is, your x min direction is electric, then the opposite x direction is also electric ET0. And similarly for the next two opposite faces. That's why it is called as a coupled. Here are lattice pair, and then this is auto identify lattice pair. So the new of this HFSS, there is direct option. You directly go to this in the coupled here. You can directly assign the lattice pair boundary conditions. Okay, in the global XY direction, this is created, and we can see it here in the project manager. Just go to this boundary, and in the boundary there are two lattice pair. Okay, this is the first lattice pair in the Y axis, along the Y axis, and this is the second along the X axis. Okay, both the lattice pair have assigned. Now what we have to design, we have to insert our fluctuate port along this Z axis. Okay, for that we have to choose the face of this boundary region. This region which we have created, we have to choose its boundary. We have to choose its face. Okay. For that, anywhere in this screen, just right click. Okay. This is the selection mode. If you are take in anywhere, option selection mode. In this selection mode, there are multiple options what you have to select. So for this fluctuate put, I have to select this faces. So just take this face and go to this region, this one, this face. Okay, just select it like this. Then right click here. Now we don't want to assign the boundary. Now we have to assign this excitation. To go to the excitation, port, and in port, there is a fluctuate port. Okay. This window will come, and here two vectors are there. This is the direction for A vector, this is the direction for 1, 2 vector, and both are undefined. So just click in this arrow key. There is a new vector option. Okay, select it, and in now see, this is the direction for first vector, this is the direction for second direction, and both we have defined, and here it is like in the fluctuate port 1, the same the corner edge is same, the same point we have to assign our both the vectors. Okay, after that click next. Here you can choose your number of modes, how many modes you want to simulate. So this choose this. Here it is, 2 is sufficient for TE and TM. Just next. Okay, next, and then finish. So one port we have designed. This is the in the project manager. Just go to the excitation, and there is a plus symbol. See, this is my first fluctuate port. Okay, now we have to design our second fluctuate port. For that, we have to do the same process for this lower edge, the lower surface, lower Jadmin surface. Okay, so it's better to first move this region so that you can able to select this Jadmin face. Now, this is sufficient for right click here, selection mode, go to face, and take this face, select this face, right click here, assign excitation, then port, then fluctuate. All the things are similar. Now, as we designed our fluctuate port in the upper ZMAX side, the same vector is defined here. Okay, this is name is fluctuate port 2, and the both the vectors are already defined here by default. Similar things, just save, next, and finish. Okay, this is the fit axis, rotate. Now this is the complete fluctuate port designing and the boundary condition assignment for this structure. Okay, right now I am directly, this excitation is the same process. We have to choose all these excitation fluctuate port in the ZMAX direction and the Jadmin direction like this way only. But there is an option, because if this HFSS is not latest version, then it may be possible that the auto lattice pair option is not there. So we have to choose one by one surface, and we have to apply the lattice pair, master slave pair. Okay. So this is the complete structure, and we have assigned all the boundary and excitation. So now we have to, for the simulation, we have to validate our structure, whether the structure and with the with the dimension value of this structure, all these other settings are applied or not. So for that, just in this section, just go to the simulation part, and here in the simulation, you have to validate your structure first before the analysis. Before the simulation, first you have to validate your structure. Okay. Just here, all the other things are completed, the boundary and excitation, mesh, 3D models. Only this analysis setup is not completed, not validated. So we have to check it from here, this analysis part. Just right tick. Okay. Add solution setup. This thing is okay. This is see. Here this sweep types. You can also make this auto solver setting from balance to higher accuracy. Okay, this is up to you. You can choose this higher accuracy or you can choose this balance. The sweep type is discrete. Okay. Linear count, and you can also choose this linear step. Okay. This is our starting frequency. This is our end frequency, and we can also change this at any time. And the step size is 0.02 gigahertz, and the sweep type is discrete only. Okay. This validation is completed. So now we can simulate this structure. Just take this, analyze all, save this project. I just delete all the previous messages, which is there in the previous simulation, so that if any new message will come, that will shown in this message manager section. Now the simulation is started. So after the simulation, we just have the S parameter, just like in CST. Okay. and after that we can calculate our absorption value using all these S parameters that we will see after this simulation. So the simulation is completed. Okay. The simulation part is completed. Now see, here's the result section, but no plus symbol is there. So just right click here. See directly in CST, directly you see the S parameters and you just tick this and you can observe all the S parameters which are but here just go to this result section, right tick, then in the create model solution data report, rectangular plot. Okay, in the rectangular plot this window will come and here all these category are there, whatever you want to see. I am interested in S parameter only, so just tick this S parameter, and in this S parameter, all the S parameter based on your geometry, based on your excitation port and your number of mode which you are selecting at the time of simulation, all these combination will come. Okay, and this is the unit for this result. Whether you have to choose this S parameter in dB or you want your S parameters in magnitude. So right now I am interested in magnitude. Okay, you can choose one parameter, one S parameter, and then this magnitude term, or you can directly select all these terms. Okay, so all these terms will come in this project manager. Okay, and here see in CST there is a ZMin and ZMax term, and then there is a bracket term which shows its polarization. Here the complete term is in value thing, like this is fluctuate port 1, this is fluctuate port 1, this is fluctuate port 1. That means our incident signal will come from this fluctuate port 1 and it is observed at 1 only, this term, this first one, and after the second term is representing its polarization, like this is mode 1, this is from one mode to same mode, this is port mode 1 to mode 2. There is a cross polarization between these two terms. Okay, both the terms are these two, both the terms are S11 only, because fluctuate port 1, fluctuate port 1, here also fluctuate port 1 input is and the output is fluctuate port 1 only, but this is 1 to 1 polarization reflection and this is 1 to 2 reflection. Okay, just click all these 4 parameters which are important for the calculation of the absorption curve. Okay, just observe all I don't want in terms of dV, I just want in terms of magnitude. That's why I just delete all these results. And again, I am find its value. After seeing these results, I just come. %100 reflection is there. Wait just a minute. I just see why there is 100% reflection is there. 100%. Okay. All the other terms is all the other terms are 0, which is okay, but why this S11 is reaching towards nearly 1? That we will find just a minute. How to plot permittivity, permeability. In HFSS, you can't directly plot the permittivity and permeability. So the better thing is first observe the S parameters, and then you can, by using the permittivity and permeability formula, you can observe its permittivity and permeability value. By the S parameter, you can calculate. Okay, we are again simulating this structure because as you observe, this design is in micrometer. Okay, the design is in micrometer. That means our structure should be uh, resonate in terahertz region. But we are in this analysis section in the project manager when we are analyzing in the analysis section. at gigahertz. So we can to the end of this simulation. Yeah, bye. Now all of you can see on the screen you have four S parameter plots in the magnitude form. One is your S11. This is your co-reflection. Fine. Then you have another plot, flocket port 1 ratio 2, comma flocket port 1 ratio 1. So this means this is reflecting mode, but or we can say that the reflected signal is at the port 1 only, but in the cross polar mode. Okay. Similarly for whereas your transmitting mode is flocket port 1 and port is 1 and the mode is also 1. Okay. Then remaining two, they are the transmitting signals. Okay, or transmission coefficients in which flocket port 2 ratio 1 is mode 1. Similarly, and flocket port 2 mode 2. Now, what about the absorption? How to see the absorption? Right click this results, then go for output variable. Okay, give the name of absorption. Fine. Now we have written the expression 1 minus. Now you will select the signal which is supposed to be written in this expression. So flocket port 1 mode 1, flocket port 1 mode 1. Its magnitude part, insert this. Fine. You can go for this one. Okay. Minus flocket port 1 mode 2. Okay. Again, you will insert this expression minus minus. Okay, now we have written the entire expression for the absorption. So just add this. Okay, our expression is added. Now what you can see, we'll go to this, right click this results, then again create model solution data report, rectangular plots. Now you can see there is one more option of output variables. Okay, we have written the absorption, selected the absorption, and then again ABS, that is absolute value. When we clicked on new report, we got a absorption. Okay. Now, when you want to go for field distributions, okay, so what you have to do, you have to assign some near field distribution, near field setup also. Okay. And as per the query there, if you want to create a array of this unit cell, so what you have to do, go from this mode, okay, right click this, edit, and now you have three options are there: along line, along axis, and along mirror. Okay, if you go with for reflection along line.
So what you will do, just click on this. Okay. Then go to this duplicate. Now, duplicate a long line. Okay. So how many numbers we want? We want the 3. Okay. Once we click this OK, so we are getting 3 arrays are 3 units are created. Okay, what we have done, we have just selected this structure. It should not be non-model. It should be in model form. Okay. Okay. Now you can see when we selected all the individual boxes, that is your ground, square, substrate, and region. Now, for and we have duplicated them along the y-axis. Okay, what we have done, we have just selected this vertex and then extended it to the second vertex on the along the y-axis. Then we got a dialog box in which we mentioned how many duplicate copies we need. Okay. Now what we will do, we will select them. Okay. And now we again want to duplicate them along x-axis. So again we will go for duplicate along line. We will select this vertex. We will go up to this point. Again, you can see the dialog box. You can enter the number of elements you want in that row or column. Okay. Now, okay. So you got this array. Okay. Now if you want to see the region, now you can see in this all the components, subcomponents are getting duplicated, but your region in which your overall structure is confined, that is just expanding in all the directions. Okay. Now what about the fluctuate port? Fluctuate port is there. Okay. You can simulate this. Okay. In this manner, you can get the array of unit cell from one unit cell. And for calculation of this permittivity and permeability, you have to enter the or insert the equation of for calculation of this permittivity and permeability in terms of S parameters as we did for absorption.
Okay, after this array structure, again we come back to our unit cell design. Okay. In the previous simulation time, I just told you this is the by default lattice pair, and this is the by default boundary condition applying with the help of the new HFSS setups. But if somebody have the older version of HFSS, then they must have select each separate parts individually. So for that, how we can do those terms? Suppose right now first I am assigning the boundary condition in the y direction along this for this phase and for this phase. Okay. So what we have to do? First, we have to select this. In the earlier, we just select the complete region and then select the boundary, coupled, and auto identify lattice pair. But here we can apply auto identify lattice pair directly. Okay. So what we have to do? Selection mode, select this phase first. And if you select this phase first, then after this phase, just select the opposite direction phase. Okay. And you can also select this perfect E and perfect H also, depending upon your requirement. Okay, okay. Just select this term, this phase, and press the control. Then using this rotate, just rotate this, and again selection mode, pick face. Select both the faces, both the opposite faces simultaneously. Lattice pair 1. Next, phase 0. See in the boundaries, this lattice pair is first lattice pair is applied. Okay. This is the second way how you can assign your boundary, or you can use the now in the x-axis we have to choose our second lattice pair. Again, go to using this rotate. If you try to directly select this face, this will not selected. Okay, so you have to go to selection mode and choose this face, or you can tick directly F key because it is showing all the faces. Okay. You just take this face key and select the another opposite coupled faces like this. Okay. And then right tick, go to the assign boundary, then the coupled and this lattice. This is lattice pair 2. Okay. Now see this boundary. In the boundary, both the lattice pair are there. Okay, it is there. Now for the excitation, the similar thing you have to do. Just take this face, right tick, assign the excitation port, then fluctuate port, and choose your vector here. In the one direction, I just choose this, and here. Okay, you can also see both the fluctuate port, both the for the first fluctuate port, both the vectors have assigned. This part I have already covered, so without wasting the time. Next, here it is, the number of mode. You can choose, if you choose these two mode, then the polarization state is mode 1, mode 2, this is TE, this is TM, and the MN is 0, 0 and 0, 0. If you choose 10 mode, then all the other mode. But it is enough to analyze with the 2 mode. Now using this rotation key, go to the selection mode, then face, select this port, and go to the excitation. Mainly two things is there. One is assign boundary and the another is assign excitation. Okay. This is already defined. Next, mode 2. Next. Okay. Again, the analysis setup, there is an issue with this. So right click here. This is from 0.1 terahertz. Okay. Oh. See this adaptive in the adaptive solution. This is okay. Now this problem will resolve. Okay. Clear message. This when you are right click here, then clear message for HFSS design 1. So that if any new messages occur, that will show in this box. After this analysis, after this simulation, your results will come and you have to go to rectangular plot, and initially you can only check the S parameters and all and other BSWR and another things which is already available in this HFSS. But if you want to make any other equation, then here only you have to go to the output variable, and in this output variable you have to put your equation with the help of all these S parameters. and you can analyze these things as well. Okay. One more thing is remaining for this HFSS, which is the optimization of your geometry. Okay, how we can in this EST there is an option parametric sweep. We directly go to the parametric sweep. We assign our variable and we choose the starting and ending value of that parameter, and with the help of the step size and number of samples we can analyze the parametric sweep of any parameter which are used for any design. Okay, but in the HFSS there is this term in this project manager. There is a optimetrics. I just show you after this end of this progress. You can observe your S parameters. S parameter. All these force, the magnitude part. It is always simulating from the higher frequencies. In between this simulation, if you have any query regarding the CST and HFSS, then you may ask. Again, there is a mistake by choosing the starting and ending frequency. Because we know our structure is resonating at around 2 terahertz. And we are simulating it from 2.5 to 7.5. And all these frequencies are the wastage. So better we just start our simulation from 0.5 to 3 only. The result rectangular. See, with this green curve, we can observe there is a small amount of cross reflections as well. Which is mainly useful in case of polarization converters. Okay, that means our structure is resonating at 1.25 terahertz, and by optimizing this setup, by optimizing this design, we can observe the S parameters which is below 0.3, 0.2, 0.1, so that we can get the maximum absorption output at that frequency. Okay. After this result, we will analyze the how we can optimize this design by using this optimetric. Just a minute. For this result, if you are only considering this co-polarized S parameter, co-polarized reflection coefficient, then you will not get the exact absorption formula, absorption curve. You have to consider both the terms in your absorption formula. Then only you can achieve the perfect absorption result. What exactly you get. Okay. Now the simulation is completed and we have all the S parameters. Okay. Now we just, with the help of this optimetrics, just right click here and you have to add your parameters here. Okay. With the help of this parametric, now go to this add section. Now in this after this add section here, all the variables which you are using in your design, that will come. You just choose this variable and it's depending upon you what type of linear shape you want or direct a single value you want, that we have to decide. And if you choose this linear step, then there is three terms. One is starting, what value you from where you have to start this variable. This is the start value in micrometer, this is the stop, and this is the step size, same as in CST. Okay, the step size, if I'm this 5 to 15, okay, add this is there, then okay. Okay, now in CST, there is directly a simulation button is there. You can directly choose that simulation button and you can start your simulation. But here, just add your parametrics variable here, and again you have to go to this simulation part and you have to analyze your structure. Okay. And if you want to analyze another parameters, another variable, then
See, in this case, we have already added one parameter, that is your L. If you add one more parameter, suppose TG, okay, and your nominal value, which is 0.035 micrometer, right? This is the value which you have assigned to this variable while designing the structure. Okay, so we have taken this value, okay, and now I'm going for linear count. So I want 3 portion. I am taking the count to be 3. So you can see now you have two variables at a time, L and TG. Now you can see the combinations, what combinations are coming out. Okay. Now I want to remove, suppose these parameters, I have removed them. This was not the option available in the CST part. Okay. Now what I have done, I am removing this one. Right. Now in this, what you have to do for every variable or every parametric analysis, you have to add one more parameter, one more sequence like this. Okay, like this. 2, 3. If you will add one more variable in this, then what will happen? It will make the combinations of both the variables together. And in this way, you can see for each value of L, that is 5 to 15, you can see all the values of TS are running out. So there are certain changes with respect to CHP, but you can optimize in this manner. If any participant is having any query, you can ask right now. And in this, for the simulation of unit cell, for simulating the array of unit cell, you have to assign the electric field boundary and the magnetic field boundary instead of this lattice pairs. Then only you can go for simulation of array of unit cells in HFSS, and the web port will be this locate port will be replaced with your web port. Any other queries, anyone? You can ask a question right now. See the lattice pair. Okay. Any other for explaining that lattice? See, it is the assignment of unit cell boundaries in HFSS. As we did the unit cell boundary in CHT, similarly in this HFSS, there is lattice pair in the advanced version, and in the prior versions, it is named as master slave boundaries. Port assignment to array of unit cell. It will take time, so we can discuss that thing later on. Because after this port assignment of array, there will be a possibility of simulation also, which will take a lot of time. Anyone else? Any questions? I guess there are no more questions. So let's go with the assignment of lattice pairs again. See what I'm doing. I have clicked this region. Okay. Assign boundary. Okay, one more thing. In this, you can see the model network solution type. If we change the solution type to terminal, okay, then you can see in this project manager there is no excitation, because in case of terminal network you cannot assign all the web flocket port. Okay, so for analyzing any meta surface or meta material, you have to change the solution type to model, otherwise it will not work out. Okay, now when I'm going for boundary assignment, assign boundary, coupled, okay, and then I can go for auto identify lattice pair. So it has already assigned the lattice pairs. Will it run now, or something is missing in this? Anyone? See, if you check it, there are two issues: boundaries and excitation and analysis setup. Okay. So I have cleared the messages. Fine. Now I have to assign the excitation. So what I will do? I will again select the phase. I will assign it excitation, rocket port, 3. Now I'm assigning this excitation rocket port. Fine. First one I have done like this. Okay. And the second one, suppose I forgot this point and I have assigned it from here. What it is showing? Now it is going for the inclined excitation. Okay, this may lead, this will be useful for circular, for calculation of axial ratios or circular polarization convergence. Okay, so what you have to do? Simply use this one. Okay. Now in this you can see there are multiple number of modes are being asked. So if you check and change the values, what modes you want to check. Okay. Yeah. Now in C, here when we are talking about mode setup, you can see there is a mode calculator. Now how will you change the polarization angle and the incident angle? The polarization angle is phi and your incident angle is theta. So I am going for phi. Okay. And step size of phi. Similarly, theta underscore 1. You don't need to assign this phi 1 and theta 1 here. Okay. Just simply finish this. Now, how will you assign those phi and theta? See, in the lattice pairs, there is an option of phase delay. In this, you have to assign phi underscore 1 and theta underscore 1. So phi is about 0, theta is also 0. And what about this one in this? See, these are the scan angles. This will be used for this beam steering kind of things. In which plane you want to check the pattern. Okay. Similarly, we will go for citation of socket predefined. Okay. So any queries right now? If anyone is having any query regarding this HFSS or the CST, you can ask right now. We can take all the queries. See, for see, the unit cell S11 is not equal to your S22 because the structure which you are using at the yes, unit cell, you can see the port 1 is assigned when you are talking about port 1, flocked port 1. What is the structure at the top of the meta surface or this unit cell? It is a ring. Okay. So in this, at the center portion, there is a blank space, or we can say which is not covered with the metal. So some signal, incident signal is getting inserted into the substrate and only some portion is getting reflected back, which is due to the resonating structure of this square ring. Whereas when you are talking about this ground plane or port number 2, which is a complete ground plane. So the entire signal is getting reflected back. Okay. The normal incidence angle will be your 0. Okay. Because you are incidenting the signal along the Z direction. Okay. Your normal direction is along Z max to Z min. Okay. So your theta will be always 0 and that is your normal incidence angle. Except that angle, all the angles or all the values of the theta will be your oblique incidence angles. I guess I am clear about this non-equivalence of the S11 and S22 in unit cell and the oblique and normal incidence angle. And this epsilon R value will definitely affect your axial ratio because the axial ratio is dependent on the electric field value, which is directly dependent on your epsilon R values also based on the surfaces. And your TE and TM modes are when we are talking about TE mode, we talk it to be when your phi is 0. Okay. That is your E plane part, we can say. If we are familiar with the antenna, then we are talking about E plane. And for TM mode, it will be H plane. So when we are simulating this unit cell or the meta surface, we have to go for a TE mode, we always consider phi to be 0. And for TM mode, we consider the phi to be 90 degree. And for this circular polarization, see the PCRY already covered, in which we were talking about only the either the signal is incidenting in X mode or X polarized wave, and it was getting converted into Y polarized wave. Okay. If both the polarizations, that is your X to Y polarization and Y to X polarization, or we can say how to identify that, it will be if you check in terms of phi equal to plus and minus 45 degree. Both the signals should be, both polarization convergence should be equal. Then only you will get the circular polarization. And there should be a 90 degree, 180 degree phase difference between the, 90 degree phase difference between the X polarized wave and the Y polarized wave. Then only you will get the this circular polarization. And you have to check yourself how to calculate this axial ratio in this HFSS. Okay. If still you can't find out, we will tell you even after this FDP. You can mail us and we will let you know. Anyone else? Now you can see we have assigned some the parametric analysis. So how to see the value of all the parametric analysis results? Go to this. Okay. Now I can go for report. Yeah. Slow. Yeah. You can go to modify report. Okay. Now I am talking about S11 in magnitude. I will go to families. Okay. And I want to see the variations of this effect of variation in L only. So new report. So now you can see if the length was 5, it was giving me, it is currently running. Okay. And for 10, it is already there. So in that way, you can see the variations or the parametric analysis results, how it is getting changed. If you want to add all the parameters in this, like this one. Okay. Now apply trace. So now you can see in the discrete mode what is happening. You can see the variations in the all parameters with respect to variation in the parametric value. Anyone else? Any questions? And if you want to see the field, select the components, go to plot field, J, magnitude JSF. See, we have not selected the save fields for all the frequencies. Okay, so that's why it is giving me last adaptive only. Okay, and thus it is giving me 5 terabyte. If there is a sweep, then it will be giving me all the frequency points. Okay, now you will go for this magnitude JSF. Okay. Now I am going for, so what is this JSF? This is your surface current. Now in this you can see at this 5 terahertz, the current is mostly confined along the horizontal sides of the unit cell. Okay, you can even change this. Okay, you can make it modify. You can go to scale, and you want to go for log. Then it is changed into log. Okay, completely red. Okay, if I want to go for this plot field J magnitude E, this is my E field. Okay, and if I go for modify, then TP. So you can see at the ground plane, there is no current electric field. Okay, and inside the substrate, from these points, the field is getting, the signal is getting incidented, and again, it is getting this yellow and green portions are showing that the signal is getting dying out. I hope all the queries are resolved. Okay, I guess there are no more questions. So thank you everyone for your active participation in this FDP and making this FDP a success. If any participant wants to share any feedback or comment, you are welcome. Okay. Yes. Anyone else having any question? Yes, we will definitely resolve your queries even after the FDP, and you can mail it. Okay, and we will definitely resolve them and Okay, so thank you everyone, and we will try to organize such FDP in future also. We hope for your active participation that time also, and thank you everyone. Yeah, the certificates will be shared to your email IDs. By tomorrow evening, you will receive them. If you don't, then kindly mail us. Okay.